Lecture 36, Faults in Subsurface Data. Drilling through a fault results in either a repeated or missing stratigraphic section at the fault cut. For vertical wells, normal faults omit stratigraphy, while reverse faults cause repeated stratigraphy. The red arrows in the figure show the missing section for the normal fault, and the repeated section for the reverse fault. The amount of section missing or repeated at a fault cut is the stratigraphic separation. Stratigraphic separation is equal to the fault throw only if the strata are horizontal and the well is vertical. This works fine for vertical wells, as shown in Figure A. However, if as in Figure B, the well is deviated and is inclined less than the fault dip, a repeated stratigraphic section, which normally is associated with a reverse fault, can be seen in a normal fault. Therefore, when discussing stratigraphic separation, one must be careful about the well and the fault orientations. Missing or repeated section in wells can help identify faults. The figure shows missing section and a normal fault detected by log correlation of a well crossing a fault and a nearby well. The well crossing the fault is represented by the blue curves, and the nearby well with the complete section by the red curves. The stratigraphic separation is about 6 meters. Inspection of the core from the well crossing the fault reveals a damage zone with a higher density of deformation bands and slip surfaces. Dip meter logs, which record the dip azimuth and dip along the well, can also help identifying faults. Abrupt changes in dip and/or dip azimuth can be expected near faults. The figure to the left shows dip meter data from a well in the Gulfax field area. The depths indicated by the red lines labeled F are possible faults. At these depths, there are variations in both dip and dip azimuth. The figure to the right shows another example from the Gulfax area. Here, the changes in dip with depth show a cusp geometry, with maximum dip values at the fault. This is related to drag or folding around the fault. Microresistivity images can help identifying faults. Figure A is an example from a well offshore Australia, where two methods give about the same image of the well interval. The sinusoidal pattern seen in these images represent planes that cut the wellbore at an angle, as illustrated in Figure B. The dip of the planes can be estimated by the shape of the sinusoids. The fault is interpreted in A as the blue line and it dips about 40 degrees. The hanging wall block dips about 10 degrees and increases in dip towards the fault to about 20 degrees. The footwall block dips about 30 degrees and increases in dip towards the fault to about 50 degrees. Poles to these data are plotted on an equal area stereo net in Figure C, and an interpretation of the fault is shown in Figure D. There is more folding of the strata in the footwall block than in the hanging wall block. Although there are plenty core data along small faults, there are not much core data along large faults with hundreds of meters of displacement. An example of core data along a large fault is that of a well crossing a large fault in the Bragg Field, northern North Sea. There, oriented cores were taken, including the 20 meters thick fault zone. This is a unique example. Drillers are reluctant to cut cores across faults because of the risk of jamming and potential pressure problems. Furthermore, some cored fault rocks may be so loose that they fall apart. The degree of imaging of faults in seismic depends much on their dip. Seismic data are designed to image gentle surfaces. Steep faults such as normal faults are in general not well imaged in seismic. Gentler faults such as reverse faults are better imaged and can display fault reflections. For a fault in seismic, we generally don't look so much at the fault itself but at the reflectors that are offset by the fault and their correlation across the fault blocks. Discontinuous reflectors indicate the fault location, and the dip separation is estimated by correlation of the reflectors across the fault. This is an example from the Visond field in the North Sea. Notice that the seismic section is in time. Three-dimensional seismic data give an excellent description of faults in the subsurface. Here, we can interpret faults in vertical sections of any direction, or in time slices. These days, machine learning techniques can greatly speed up this interpretation. The challenge for manual or machine learning fault interpretation is to correlate the interpreted fault traces to reconstruct the faults in 3 dimensions, as well as to establish the interaction of different fault populations. The Wisting field in the Barents Sea is a shallow and faulted area. This figure shows depth seismic sections across a northeast-southwest normal fault, from A, in the southwest, to F, in the northeast. The fault and other faults in the field are displayed on a depth slice using seismic variance. Notice that the faults in the sandstone reservoir level, at about 250 meters below the sea floor, transition upwards into a fold structure in shale units, which function as the top seal. Notice as well the smaller scale faults in the Colmule Formation. These are part of a polygonal fault system. In the section, we can also see seismic artifacts. These are fault shadow zones, which are areas in the footwall block, where the reflectors are distorted. Notice that the interpreted horizons don't follow the distorted reflectors in the fault shadow zone. Faults are narrow volumes. This seismic section illustrates that. How you would interpret the fault in the seismic section. The figure to the left shows an interpretation. Key intervals are interpreted and colored, and the fault structure, which consists of several faults, is traced. The figure to the right illustrates the seismic signals that may indicate the presence of a fault. These include amplitude anomalies, amplitude reduction towards the fault, and folding of the reflector adjacent to the fault. The resolution of seismic data is low in comparison to well data. The vertical and lateral resolution of seismic data are in the order of tens of meters. In practical terms, this means that when interpreting faults on seismic data, there are always uncertainties related to the internal fault structure. How is the yellow reservoir interval on the seismic section offset by the fault? Is it by a single fault, like interpretation 1? Or is it by multiple slip planes, like interpretation 2? Or is the reservoir dragged along the fault, like interpretation 3? We can't rule out any of these interpretations, and they will have different implications for the way light fluids, such as hydrocarbons, migrate from the hanging wall block to the footwall block. Interpretation 1 rules out any migration of fluids from the hanging wall to the footwall. Interpretations 2 and 3 allow fluid migration from the hanging wall to the footwall. This is also nicely illustrated by this figure. Figure D shows the actual fault structure as observed in outcrop. Figure C shows the modified fault structure for a single fault plane. C and D can be considered as possible interpretations of the fault on a seismic section. Interpretation C rules out oil migration from the hanging wall block to the footwall block, as shown in Figure A. A well targeting the hanging wall reservoir next to the fault will encounter oil. Interpretation D allows oil migration from the hanging wall block to the footwall block, as shown in Figure B. A well targeting the hanging wall reservoir next to the fault will encounter water. To learn more about this, read Chapter 9 of Fossen, and do his e-learning module on faults. And answer these questions.